Welcome to G Fun Facts Online. Today, we are going to strip away the romance of baking and look at the invisible reality of bread. The world of sourdough is often painted in the soft, warm hues of nostalgia, a rustic tradition passed down through generations, defined by intuition and feeling the dough. But if you were to peer closer, looking through the transparent wall of a fermentation jar, you would find a universe governed not by magic, but by the rigorous, elegant, and often violent laws of soft matter physics. To the baker, it is a loaf. To the physicist, it is a complex, non-equilibrium foam, stabilizing a biological runaway reaction. This is the story of the sourdough glass. We are using this term as a triple entendre. It refers to the glass jar that allows us to witness the birth of the foam, the glassy state of the shattering crust that encases the finished loaf, and the metaphorical magnifying glass we must hold up to understand the forces at play. From the moment flour meets water to the final crackling song of the cooling loaf, we are witnessing a masterclass in rheology, thermodynamics, and polymer science. Let us begin with the genesis of the foam, specifically mixing and nucleation. The life of a sourdough loaf begins with a paradox, which is that yeast cannot create bubbles. It is a common misconception that the carbon dioxide produced by fermentation blows up the balloon of the dough from scratch. In reality, carbon dioxide is unable to overcome the surface tension of the dough's aqueous phase to form a new bubble spontaneously. The pressure required to nucleate a gas bubble de novo, or from nothing, in a liquid is astronomically high, far beyond the capabilities of a single yeast cell. Instead, the bubbles that will eventually become the alveoli, the holes in your crumb, are born during mixing. This is the nucleation phase. When flour and water are combined and agitated, whether by hand or a spiral mixer, atmospheric air is folded into the sticky mass. These microscopic pockets of air, primarily nitrogen and oxygen, are trapped within the developing gluten matrix. They are the seeds of the loaf. Without them, the yeast would produce carbon dioxide that would simply dissolve into the water and eventually diffuse out of the dough, leaving you with a flat, dense puck. The physics of mixing is thus a race against time to occlude as many microscopic nucleation sites as possible. The structure of the final crumb is determined right here. A high-speed mix creates a proliferation of tiny, uniform bubbles, resulting in a sandwich bread texture, while a gentle hand mix or slow fold preserves fewer, larger, irregular bubbles, creating the chaotic beauty of an artisan loaf. Before this foam can stabilize, however, the stage must be built. This is the realm of hydration physics. Water is not merely a solvent. It is a plasticizer. Wheat flour contains two key proteins, gliadin and gluten. In their dry state, they are inert, tightly coiled, and glassy. When water is introduced, its polar molecules, or dipoles, insert themselves between the protein chains. This lowers the glass transition temperature of the proteins, transforming them from a rigid solid into a pliable, cohesive system. The gliadins acts as a viscous solvent, providing fluidity, while the glutenins link up via disulfide bonds to form a vast, elastic network. This network forms the walls of our foam. In a high hydration sourdough, say 80% water content or more, the physics shifts dramatically. The dough behaves less like a solid and more like a non-Newtonian fluid. The abundance of water increases the mobility of the polymers, allowing for greater extensibility, but it also dilutes the gluten network, making gas retention more precarious. The baker must balance the lubrication required for expansion against the structural integrity needed to hold the foam together. Once the mixing stops, the biological engine, the sourdough starter, roars to life. A sourdough culture is a symbiotic ecosystem of wild yeasts and lactic acid bacteria. As fermentation begins, the yeast metabolizes simple sugars and produces carbon dioxide and ethanol. The carbon dioxide enters the aqueous phase of the dough, which is the water trapped in the gluten network. Here, Henry's law takes effect. The water becomes saturated with carbon dioxide. Because it cannot form new bubbles, the gas seeks the path of least resistance, which are the pre-existing air bubbles created during mixing. Driven by concentration gradients, carbon dioxide diffuses from the liquid dough into these nitrogen gas nuclei. The bubble expands, and the dough rises. Simultaneously, the lactic acid bacteria are not idle. They produce lactic acid and acetic acid, lowering the pH of the dough from a neutral 6 down to a tart 3.5 or 4. This acidification is not just about flavor, it alters the physics of the foam. Gluten proteins are sensitive to pH. As the environment becomes more acidic, the net positive charge on the protein chains increases. This leads to electrostatic repulsion between the chains, meaning they push away from each other. This unfolding effect softens the gluten, making it more extensible or stretchy. However, too much acid or over-fermentation can degrade the gluten completely, turning the dough into a proteolytic soup that cannot hold gas. The jar we watch is a monitor of this delicate balance between expansion and degradation. This leads us to the physics of foam stability. Why does the foam not collapse? A bowl of soap bubbles pops in minutes, yet a sourdough loaf must hold its structure for hours. The stability of sourdough foam relies on two distinct physical mechanisms. In the early stages of fermentation, the bubbles are spherical and separated by thick walls of dough. The stability here is provided by the viscoelasticity of the gluten starch matrix. Viscosity, the liquid-like behavior, allows the dough to flow and expand as the gas pressure increases. Elasticity, the solid-like behavior, provides the restoring force that prevents the bubble from bursting. The key property here is strain hardening. As the bubble wall stretches, the gluten polymer chains uncoil. Once they are fully extended, they resist further stretching, causing the material to harden or become stiffer. This is crucial. If a thin spot develops in the bubble wall, strain hardening ensures that this spot becomes stronger than the surrounding thick areas, preventing rupture. It is a self-healing mechanism built into the chemistry of wheat. As the dough expands further, the walls between bubbles become microscopically thin. The starch granules, which are large rigid boulders compared to the gluten strands, can disrupt the network. The gluten film may actually rupture. Why does the gas not escape? Recent research points to a secondary stabilization mechanism known as liquid lamellae. A thin film of liquid, stabilized by surface active agents like polar lipids and soluble proteins present in the flour, forms a bridge across the gaps in the gluten network. This is identical to the physics of a soap bubble. These surfactants lower the surface tension at the gas-liquid interface, preventing the film from draining and collapsing. If you look closely through the glass of your fermentation jar, you might notice that large bubbles seem to eat the smaller ones. This is a phenomenon called Ostwald ripening, driven by Laplace pressure. The pressure inside a bubble is inversely proportional to its radius. Smaller bubbles have higher internal pressure than larger bubbles. Consequently, gas diffuses from the high-pressure small bubbles into the low-pressure large bubbles. The small bubbles shrink and vanish, while the large bubbles grow. In sourdough, this creates the characteristic wild crumb, an irregular landscape of massive caverns and tiny alveoli, contrasting with the uniform crumb of commercial yeast bread, where fast proofing limits this physical migration. In modern sourdough physics, the container itself has become a scientific tool through the aliquot method. Bakers pinch off a small piece of dough and place it in a small, straight-sided cylinder to monitor expansion. This creates a controlled physical system to measure volume expansion. The physicist baker knows that time is a poor metric for fermentation because it is dependent on temperature, following the Arrhenius equation. A dough at 21 degrees Celsius ferments half as fast as one at 27 degrees. By observing the aliquot jar, the baker measures the result of the kinetics, the gas production, rather than the input of time. When the dough in the glass increases by 30 to 50%, the foam is at its limit of stability. The gluten network is maximally extended, but has not yet reached the fracture point. This is the moment of baking. The transition from foam to sponge occurs in the oven. This is a violent, chaotic event known as oven spring. As the cold dough hits the hot stone, often at 250 degrees Celsius, heat transfer begins. The crust heats rapidly, but the center lags behind. Three physical forces drive the sudden expansion. First, thermal expansion, or Charles' law. As the temperature of the gas inside the bubbles rises, the volume increases. Second, a solubility drop. Gases are less soluble in hot liquids. The carbon dioxide dissolved in the dough's water is suddenly forced out of solution, rushing into the bubbles. Third, evaporation. Water and ethanol flash into steam. Since water expands roughly 1,600 times when converting to steam, this provides a massive kick of pressure. However, there is a limit. At roughly 60 to 80 degrees Celsius, the starch granules begin to absorb water greedily and swell, a process called gelatinization. They lose their crystalline structure and become an amorphous gel. Simultaneously, the gluten proteins denature. They unravel and crosslink, coagulating into a rigid structure. This is the critical setting of the foam. If the gas pressure expands the bubbles before the starch sets, you get volume. If the starch sets before the gas expands, the loaf is constrained. This is why steam injection is used in ovens. It keeps the surface temperature low and the crust flexible to allow this expansion to happen. Finally, we arrive at the true sourdough glass, the crust itself. As the surface of the dough exceeds 100 degrees Celsius, all water evaporates. The dehydration is extreme. The starch and protein on the surface undergo a phase change. At 140 degrees Celsius, the Maillard reaction begins. Amino acids and reducing sugars react to form melanoidins, complex ring compounds that give the crust its brown color and roasted flavor. As the crust cools, it enters a glassy state, a process called vitrification. In physics, a glass is an amorphous solid, a material that has the disordered molecular structure of a liquid but the mechanical rigidity of a solid. The sugars and gelatinized starches in the crust, now devoid of the plasticizing water, lock into place. The singing of the bread. The crackling sound heard as a loaf cools is the sound of physics. The crust is in a glassy, brittle state, while the crumb is in a rubbery, soft state. As the loaf cools, the crumb contracts slightly. The glassy crust cannot contract. Tension builds up until the glass fractures microscopically, creating the snap, crackle, and pop. The sourdough glass is not just a container, it is a lens. It reveals that the humble loaf is a triumph of soft matter physics. It is a foam, generated by biological machines, stabilized by polymer networks, inflated by thermodynamic expansion, and frozen in time by a glass transition. Understanding these forces does not diminish the romance of baking, it elevates it. When you hold a slice of sourdough up to the light and admire the open, glistening alveoli, you are not just looking at bread. You are looking at a record of nucleation, diffusion, strain hardening, and the delicate dance between the rubbery and the glassy states of matter. You are eating physics.